Good morning and welcome to this second course on partial differential equations. And this is a continuation of our first course on partial differential equations. So before trying to attempt to take this course or want to learn this course, we strongly advise you to go through the course PDE1. On the other hand, if you are already familiar with the course PDE1, you may directly look into this course. So it's not really an advanced course, but it's a first course. So the PDE1 and PDE2 together consists of one full semester course. So what I'm going to give in this introduction basically consists of two parts. I will quickly in 10 minutes or so, I will try to give a brief overview of the PDE1 course which we have covered, and then I will give a brief introduction to the course on PDE2. And so let's begin with what we have done in our NPTEL PDE1 course. So let me quickly review through the one. So we began this course by giving a basic introduction to the PDE and some preliminaries required. So again, we advise the students to go through the preliminaries mentioned in our PDE1 course, especially the understanding of the domain and its regularity and integration by parts, especially the Gauss-Green theorems and Stokes theorems, and the basic analysis from that, convergence, uniform convergence, and various other things involved in elementary thing. It's important to understand the regularity of the domain, the existence of the normal derivative and normal directions, and then how do you integrate by parts in higher dimensions in omega. And you know integration by parts in one dimension, but you also need to know how do you do this one. So various fundamental theorems like Gauss-Green's theorem, divergence theorem, and all that, please get familiar. And that is what we have done it in first to 6 lectures of our PDE course. And then we have introduced what is called the first order equations in 2 or more variables. One of the main thing we concentrated is the notion of characteristic. By the time you would have gone through the course PDE1, you would have seen the importance of the characteristic concept in partial differential equations that even goes to the next section, what are called classifications. So initially we are given a detailed analysis of your first order equations in starting with the 2 dimensions and then later on higher dimensions, and we also introduce in a systematic way about the first order equations, about method of characteristic, first doing it for the linear equations and then for quasi-linear equations and then higher linear equations, and various geometric concepts including Monge cone and Monge strips, integral surfaces and all that. Okay, and then in the process you also seen to motivate how the non-classical solutions exist, especially when you dealt with the quasi-linear equations. You have seen the conservation laws, and this course you will see more about the specialized first order equations, which we will slowly describe. And based on that, we have it's unlike ODE. ODE is basically classified into linear and quasi-linear, linear and non-linear, but then you have seen that's not enough for PDEs. The using the characteristic and non-characteristic Cauchy problem led to various classifications like elliptic, hyperbolic, and parabolic. Even linear equations, you will have this type of classifications. You have seen it. But then after that we explain 3 important equations. We are given the motivation why we study these 3 important equations. These 3 equations, namely elliptic, parabolic, and hyperbolic, is a representative candidates, a Laplace equation and heat equation and wave equations. And the idea all these equations arise in the literature as it is. That's one reason why we study these 3 equations. And we also seen these equations are representative things like of equations because it has all the characteristic of the equations belongs to that particular class. For example, Laplace belongs to the elliptic class, heat belongs to the heat belongs to parabolic class, and then wave equation belongs to the hyperbolic class. But what we have done in Laplace and Poisson equations very minimal in the first course. The main idea was to introduce the fundamental solutions, Green's function and mean value property. We have not done the solvability much, except very little solvability in one or two specialized cases, and we will see more in the coming course, which we will explain soon now. Okay, so the important thing, you have to recall all these results, go through it. Even if you have studied the course 1, please go through the Laplace and Poisson equations and especially understand fundamental solutions, the mean value property, and Green's function. Special Green's functions we have introduced for upper half plane and a circle or a sphere, which plays a crucial role in the solvability of the Poisson equation. And we have seen the other important things called maximum and minimal principles. So you have to go through all that quickly. After that, we have done 1D heat equations and 1D wave equations. Okay, so 1D in the 1D wave equation we have seen and wave equations we have seen some of the physical applications, and we also seen the heat ball and fundamental solution and maximum principles, and you also seen in the first course the solution by Fourier method. In 1D wave equation, you have derived using the separation variable formula, the D'Alembert's formula you have done, and how it is. The more important thing is that wave equation plays something is so much differ from the Laplace equations, and wave nature of the solution, like propagation, like finite speed of propagation, characteristic parallelogram, and you have also seen Duhamel's principle in equation in infinite dimension, in semi-interval. So you have seen various things. So we have only discussed heat equations and wave equations in one dimension. On the other hand, you have seen the Laplace and Poisson equations. We have introduced the fundamental solutions and all these property even in n dimension. That was the rough idea discussion about the review of our first order PDA. So let's now go to what we are going to do in this course. As I said, the first lecture is about the review of this course and also an introduction to that one, and that we will do it in this half an hour lecture. And then we are going to discuss two important first order equations. Okay, both these equations are first order equations. Okay, this is called the famous Hamilton-Jacobi equation. And here you will see the conservations of this is a first order equation, a special first order equation. In fact, this is a family of equations. It's not one equation, a class of equations. Okay, and this appears from various things. So we are not going to do Hamilton-Jacobi equation. So Hamilton, more generally Hamilton-Jacobi, there are other generalizations like Hamilton-Jacobi-Bellman equation and Hamilton-Jacobi-Isaacs equation. We will not be discussing. So the Hamilton-Jacobi equation is a more of a classical equation coming from calculus of variations. And on the other hand, this comes from optimal control problems. Optimal control problems. And this comes from differential game theory. As I said, we will not do it in a very generality. This is a very special type of nonlinear equations which doesn't have in general the variational structure. So our main idea is to derive what are called the Hoff-Lax formula, which is a very special formula, very special case So we will be deriving the Hoff-Flax formula, which gives you a formula for the solution of the Hamilton-Jacobi equation. Typically, the Hamilton-Jacobi equations will have this form, where H is called a Hamiltonian. We will motivate you through various examples. So, and there are more general. So this is a very special class of equations arising from more general nonlinear equations. And you have seen that you will see again here the discussion of the uniqueness, and we will not be able to prove the uniqueness results, which you may refer to the one of the books which we suggest. But the important thing is that you get uniqueness, but uniqueness not in general. So you have to get into the kind of what we call it weak solution concept. So you will see here in this case one type of weak solutions, but that's not enough. In general, when you want to go into more general equations like Hamilton-Jacobi, Bellman equation, now Hamilton-Jacobi equation. So there is a big general theory, what we call it a viscosity solution. So we will not touch that concept of weak solutions or viscosity solution. This viscosity solution concept is different from your weak solutions, which you are normally look for using Sobolev spaces. Similarly, this we will do it in a 2 to 3 hours, maybe half an hour lecture. And similarly, there is another first order equation. This is also first order equation or first order system, first order equation or system, and we derive again a representation of this one, what are called the Lax-Solenic formula. So you derive, and again we will discuss about brief discussion about the uniqueness, and we also discuss about the system of conservation law and Riemannian invariance. By the way, this course is going to give two of us, my colleague Professor Datti and myself, just like what we have done it in our first part of the course. So the conservation laws is another special class of equations of this form, UT. So you have a conservative structure or the variational structure. And you have already seen this equation, special case. UT equal plus UUX equal to 0. This is the Burger's equation. And you have seen in our first course how singularities propagates. Singularities. And you have to understand the singularities. You need to go through what are called the weak solution concept. So we will do, in fact, what I said, what we will do is very, very minimal. You can spend all your whole life in conservation. So in this case, so we will also try to do little bit about the system. Systems are very, very interesting in conservation laws, and you also be introduced to what are called Riemannian invariants. So after these first order equations, this is the continuation of our first order thing. Two types of first order equation, Hamilton-Jacobi equation and conservation law. And then we will go on to study the three equations again, more general. So let me briefly tell you what we have done in the Laplace equation. Our aim is to study this, is that thing. Our aim is to study Laplacian equal to U equal to F in a domain omega. And then you want to study U equal to G on d omega. And in our first course, you have studied that you can represent the solution. This you can be written as U is equal to V plus W. And then you can solve these two equations, minus Laplacian V equal to F, and then V equal to 0. So you split it into two things. So you have a non-homogeneous equation with a homogeneous boundary condition, and then you will have the other W will satisfy, minus W equal to 0. So this is a homogeneous equation with a non-homogeneous data. This is in d omega. So you can write, so instead of studying this equation, the equation 1, you can study this equation 2 and you can study these equations 2. So 1 is studying is equivalent to 2 and 3. You see, you can study that equation. So what we have seen in this first equation and glimpses of this equation 3. Okay, and that also in a very special domain. Okay, when omega is in course 1, we have seen when omega is equal to a ball or an upper half plane, we have introduced the Green's function and we have solved omega is equal to 1. So when omega equal to ball or upper half plane, we have studied 3. Studied 3 in course 1, in PDE 1 course. So what we will do, the existence uniqueness, not in the full thing discussion, existence uniqueness, etc. Existence uniqueness. In a more general setup. So outside that, and that is via the Perron's method. So we will spend some time, and again we will not do it in very detailed way, but we will try to introduce what is called the Perron's method. So Perron's method is to the study of the equation 3 with a non-homogeneous equation with a non-homogeneous data on the boundary. Okay, so you have on the boundary, you have a non-homogeneous theta. This you cannot do it, you cannot impose a boundary condition for arbitrary domains. So there is a notion of called boundary regularity. So we will introduce the concept of boundary regularity and we study the existence and uniqueness for the homogeneous equation. I think that. But then we have another part. So let me discuss this now. I don't want to take another page here. So you want to study this equation, and this equation we called what is study the potential theory. So you have to study this what are called the potential theory, and this is the basis potential theory. So this is the basis for leading to general second order equation, what is called a Schauder theory. We will not get into the Schauder theory, but even understanding the potential theory, basically minus Laplacian u equal to f, we want to study. The problem is that when you want to study, so normally we look for a solution V in C2 space. So V in C2, for example, if you study V in C2, this typically implies minus Laplacian V equal to f in a continuous function. So it's very natural to look for solutions when f is continuous. But unfortunately, just f continuity is not enough. F continuity in C is not enough. You will see this important thing. You need enough to solve the problem. You see, so that's something a bit of a surprise, because when we have V equal to 0, Laplacian V equal to f, so you expect to solve when f is a continuous function. But so you need little extra regularity. And so you, of course, if f is a C1 function, that's what we have mentioned here. When f is a C1 function, you will be able to solve it easily. But then that's not enough. F is C1. F is C1 is good enough, but that is a too much regularity. You want to solve it when f is in C. So you need some sort of an extra, not as much as C1. You will easily be able to solve it, but not continuity is not enough. So this introduces a new concept called a Helder continuous functions. So we motivate you why Helder continuity is required. This is exactly, if you look at the first course on our PDE, where you introduced the fundamental solution, and in the fundamental solution and its derivatives are locally integrable. But when you take the second derivative, and that's more important, because when you face a fundamental solution, you are interested in taking Laplacian of phi, and then Laplacian of phi is involves second derivative, and the second derivatives are not locally integrable. This causes trouble. So this extra regularity on the functions is precisely to take care of the non-integrability part of your second derivative of fundamental solution. These things will be discussed in the one part of Laplace and Poisson equations, and then we will also give a this is equation is nothing but Laplacian of u plus u equal to. So we also discuss Cu for a constant. So we will discuss these equations and we will discuss especially Laplace equations in spherical and cylindrical coordinate. You know, as you said, that you want to understand your operator in spherical coordinates and cylindrical, what we are so far doing in Cartesian coordinates. So we will have some set of lectures, maybe 4 to 5 lectures or 6 lectures on the Laplacian in spherical. And then we will go on to do the continuation of our heat equation. Heat equation, basically heat equation is in higher dimensions. Heat equation in higher dimensions. This is somewhat you will do it in a similar fashion as we have done. For the first order equation of the first one-dimensional equation. So we will also discuss about the uniqueness, maximum and minimum principle, and then you are already set the stage for the spherical and cylindrical coordinate for the Laplacian, and we will continue to understand heat equation in spherically and cylindrically equation. Then we will move to another important equation, what is called the wave equation in higher dimensions. There you will see the difference. One dimension we have studied the D'Alembert's formula and propagation of the singularities and various other properties. But when you go to higher order n greater than or equal to 2, you will see the odd dimension and even dimensions play different ways. So what you will basically, you will be discussing after the review of one-dimensional case, and of course you will see the fundamental solution of the wave equations. You will see the spherical means. Using the spherical means, you introduce the concept of solution, or you derive the solutions in three-dimensional space. And after doing that one, you will descend to what is called using the Hadamard's method of descent to study the solution in 2 dimensions. So basically you understand the solution in 2-dimensional as a equation in 3 dimension, write the solution obtained in 3 dimension, and using projections you bring it to 2 dimension, and you will see one important concept, what is called strong and weak Huygens principle. So the Huygens principle is very, very important. How the solution is actually depends on the boundary, you will see. And that's not true in thing. So you will see the special Huygens principle in 3 dimensions. The interesting aspect is that this is true for every odd dimension. So you will be able to write down the formula and solutions for all odd dimensions except one we have already studied, and that is different. But 3 and higher odd dimensions behaves differently. So you can write down the solutions for all odd dimensions, and using the method of Hadamard's method, you will come to the lower order things, everything. And as I said, you will see, if you have enough time, you will also see the derivation of solution in spherical means. So it's typically studying wave equation in higher dimensions. Okay, and you will do all that situation. Then this is the section 8, what you have seen is a weak formulation, and that's the stepping stone of a PDE to next PDE course. So this is basically step 2 next PDE course. So we will not be able to do much here, but then what we want to introduce in this through this course, what we call it a concept of weak derivative. How do you differentiate functions which are not possible to derive classical derivation? Suppose you have an L2 function. How do you really do weak derivatives and weak solutions? And this is more physical. That's what you have to understand. So we will we will give a glimpse of these things. Okay, how do you solve these equations? How do you solve this type of equations? How do you solve such equations? Or more generally, how do you solve second order or higher order equations? And you need new notions like distribution. We will not do this distribution, but we will and then Sobolev spaces. So these are all, so we will give a brief, somewhat a brief summary of this notions in maximum 3 to 4 lectures, I think a couple of hours of lectures. We know it's only very, very minimal, but we want to introduce that topic in this section, so you will come to know that there is more to be studied. There are more notions are required, more functional analysis is required to understand what a PDE is, and you will also see this is the way you eventually look into differential equations, and basically it becomes a hardcore analysis course. So that's a brief summary of this course. With that, let me, before stopping, so if we follow the same book on our recent book published in 2020, so in PDE 1, you have seen some sections of PDE, our book, PDE book, which is published by Cambridge IIC Press series. So we will be covering some more topics from that book. So with this course, this book, we will cover maybe 75 to 80% of the material of the book will be covered. So whatever advice or suggestions to all of you, please go through that thing. And then this is an other book we have written, and there is an NPTEL course also on ordinary differential equation. You can get into that. Some of the material we have already used from ordinary differential equations in learning these things. Learning especially the method of characteristics, and how do you use PDE converted into a system of ODE. There are many other, some references, there are plenty of references in PDE book. You can look into Evans, I have not mentioned it here, Gilbert and Trudy. If you just want to understand a lot about the potential theory and Schauder theory, and then many other things, and just discussing about the elliptic equation. So you can look into Gilbert and Trudinger to do that one, and other books which you have LC Evans, and there are many references given in our book. There are many other prerequisites, is exactly what I have mentioned here. If this is not enough, you can look into the thing. So this is the brief summary of our course. So as you see, if you really look into that one, so we are given an overview of our PDE review of before that. So we are again repeating, please go through these topics of PDE 1. Unless you go through this topic and understand the notions defined in the Green's function and other things, you will not be able to understand this present course. So we strongly recommend you to go through this course, and then we have seen what are the topics which we are going to discuss in this course. So I think I will stop here. So we will start our course with Hamilton-Jacobi equations from the next lecture onwards. Thank you.